Welcome to aminacademy.com. In electrical engineering, regarding Gauss law, let us do some solving problem. Look at this example. A uniform electric field of magnitude E equal 150 Newton per Coulomb exists in the space in the x direction. Using the Gauss theorem, calculate the flux of this field through a plane. Square area of edge 20 centimeter placed in the YZ plane. Take the normal along the positive x-axis to be positive. Here, flux. Look at here. Flux phi equal integral E cos theta ds. This is a Gauss law. As the normal to the area points along the electric field, then theta equal to 0 here. Also, E is uniform, so phi equal E into delta S, which is equal E equal 150 and delta S equal, that is using the Gauss law, then flux of this field through a plane, square area of edge is 20 centimeter. That is 20 centimeter square. 20 centimeter square is placed, that is area 20 centimeter square into 20 by 100, because in 20 centimeter is 20 into 100 because centimeter square, which is equal is your 30 Newton meter square. Next question. A large plane charge having surface charge density is sigma is 4 into 10 power minus 6 coulombs per meter square lies in xy plane. Find the flux of the electric field through a circular area of radius 1 centimeter lying completely in the region where XYZ are all positive and with its normal, making an angle 60 degree with the exact axis. Here, the electric field near the plane charge sheet of E is equal sigma over 2 epsilon 0 in the direction away from the sheet. At the given area, the field is given by Z in Z axis. First, E equal, formula for E equal, charge density sigma over 2 pi epsilon 0 by Gauss law. Now, area equal pi r square, which is equal 3.14 into 1 centimeter, that is 1 square, which is equal centimeter square, which is equal 3.14 into 10 power minus 4 meter square. The angle between The normal to the area on the field is 60, that is theta equal to 60 degree given. Now, according to the Gauss law, the flux equal E vector dot delta S vector, which is equal E delta S cos theta, which is equal sigma over 2 epsilon 0 rho r square cos 60. Sigma equal to 4 here. 4 into 10 power minus 4, so minus 6 here. 4 into 10 power minus 6 over 2 into epsilon 0 is 8.85, 10 power minus 12 into 60 is 1 by 2. Into here r square cos 60. Three point 14 into 10 to the power of minus 4, which gives 35 Newton meter square per coulomb. Because this radius is 1 centimeter, that is 1 square is 1. Next question. A charge of 4 into 10 power minus 8 coulomb is distributed uniformly on the surface of a sphere of radius 1 centimeter. It is covered by a concentric halo conducting sphere of radius 5 centimeter. Find the electric field at a point 2 centimeter away from the center. Then a charge of 6 into 10 power minus 8 coulomb is placed on the halo sphere. Find the surface charge density on the outer surface of the halo sphere. Here in the first case, find the electric field at a point 2 centimeter away from the center. The flux through this surface, the flux through the surface is integral E vector delta S. which is equal E delta S, which is equal 4 pi x square at distance x. Now further it is equal 4 pi x square E, where delta S equal, we can keep it delta x in x distances. Then where x equal x equal 2, that is equal 2 into 10 power minus 2 meter. From the Gauss law, this flux is equal to the charge Q contained inside the surface divided by epsilon 0, which is equal 4 pi x squared E is equal Q over epsilon 0, or E equal Q over 4 pi epsilon 0 x squared. We substitute the values, therefore here we can get it equal 4, that is 9 into 9 into 10 power 9 into 4 into 10 power minus 8 over 4 into 10 power minus 4, which is equal 9 into 10 power 5. That means here 4 and 4 cut. The second part, Newton per Coulomb. The second part we need the charge of 6 into 10 power minus 8 Coulomb is placed in the halosphere. Find the surface charge density on the outer surface of the halosphere. Take the Gaussian surface through the material of the halosphere as the electric field in a conducting material is zero, the flux. Therefore, the flux equal E vector ds vector through the given Gaussian surface is zero. Therefore, using Gauss law, the total charge enclosed must be zero. Hence, the charge on the inner surface of the halosphere, the total charge enclosed must be zero. Total charge enclosed equal to 0. Charge on the inner surface, charge on the inner surface of the halosphere is 4 into 10 power minus 8 Coulomb. But the total charge given to this halosphere, sphere is 6 into 10 power minus 8 coulomb is given. Hence, the charge on the outer surface will be the charge. Hence, therefore, the charge on the outer surface will be the sum of 4 into 10 power minus 8 plus 6 into 10 power minus 8 coulomb, which is equal to 10 into 10 power minus 8 coulomb. One more question. A particle of mass 10 into 10 power minus 6 gram is kept over a large horizontal sheet of charge of density 4 into 10 power minus 6 coulomb per meter square. What charge should be given to this particle so that if released, it does not fall down? How many electrons are to be removed to give this charge? How much mass is decreased due to the removal of these electrons? Here, the particle of mass 5 into 10 into 10 power minus 6 mass equal 10 into 10 power minus 6 gram, which is equal 10 into 10 power minus 9 kg. The electric field in front of the sheet. Now the electric field in front of the sheet is E equal sigma over 2 epsilon 0, which is equal charge density is 4 into 10 power minus 6. That is 4 into 10 power minus 6 over 2 into epsilon 0 is 8.85 into 10 power minus 12, which is equal to 2.26 into 10 power 5 Newton per coulomb. E got it. If a charge Q is given to the particle, the electric force QE acts on the upward direction. Therefore, it will balance the weight of the particle. Therefore, the weight of the particle is balanced by the charge Q, that is particle electric force QE. Therefore, here QE equal Q into is 2 into 2.6 into 10 power 5, that is QE, got it here. Then QE is balanced by Newton per coulomb is balanced by 10 into 10 power minus 6 kg into 9.8 is gravity. Meter per second square, both balanced, and therefore from equating this, Q equal 10 into 10 power minus 6 into 9.8 over 2.26 into 10 power 5, which is equal 4.42 into 10 to the power of minus 13 coulombs. The charge on one electron is, this is Q charge here. Now, charge on one electron is, that 1.6 into 10 to the power of minus 19 coulomb, the number of electrons removed. Therefore, the number of electron removed is here this coulomb divided by this charge upon one electron, that is equal 4.42 into 10 to the power of minus 3 over 1.6 into 10 to the power of minus 19, which is equal 2.8. 2.8 into 10 to the power of 6 electrons. That much electrons we need to balance the charge. Now, next, mass decreased due to the removal of this electron. Mass decreased due to the removal of this electron is 2.8 into 10 to the power of 6 into mass of one electron is 9.1 into 10 to the power of minus 31 kg, which is equal 2.6. 2.6 into 10 to the power of minus 24 kg. We have done. Please subscribe our YouTube channel.